Alright, so now we're ready to actually do these darn confidence intervals for means. There's actually two of them that we're learning here. We got a one sample z interval for mu and a one sample t interval for mu. You use the z interval when sigma is known, almost never, and you use a t interval when sigma is unknown. Vast majority of the time, usually, use the t. When in doubt, use the t. The only difference is that here you have the population standard deviation, here you have the sample, here you use a z-crit, here you use a t-crit. We don't really need to do that. So here we have an example. I kind of started it so that to shorten up the video a little bit. Feel free to pause it if you're filling out your notes. For their second semester project, Ann and Tori wanted to estimate the average weight of an Oreo cookie to determine if the average weight was less than what was advertised on the package. They selected a random sample of 36 cookies and found the weight of each cookie in grams. So the mean weight was x bar equals that with a standard deviation of that. Construct and interpret a 95% confidence interval for the mean weight of an Oreo cookie. So first step is P, the parameter step. I can't tell you how many people put P right here on the test. No, it's a mean. Population symbol is mu. Maybe it's stupid to put these P's or do these panics, but whatever. So mu is the true population mean weight of all Oreo cookies. Make sure you talk about the parameter, make sure you say what the parameter is, and make sure you put context referencing the population. Check the conditions. Random. They said they took a random sample of cookies. They're lying. They never took a random sample of cookies, but whatever. The question says they did, so we say they do. 10% condition. 36 is less than 10% of all Oreo cookies. I am sure that is true. Normal large sample. Check the sample size first. The sample size is bigger than 30, so we're good. Therefore, the sampling distribution of x bar is approximately normal. Again, probably one of the most commonly missed things is not being able to construct this. Either refusing to put it down or screwing it up, I guess. Right, so the assumptions check. N, name the test. This is a one sample t interval for mu with degrees of freedom equal to 35. This is the name of the test. You need to say the degrees of freedom somewhere in the paper, anywhere in the paper. Sometimes I put the formula with this step, sometimes I put it with the I step. The formula needs to be down there, whether you put it here or here, it doesn't matter. Formula is x bar plus or minus t crit times s over square root of n. My x bar is 11.3921. Plus or minus, I do not know my t crit, and I didn't know it when I wrote it, so I got to calculate that, so I figured we'd calculate it together. And then I put in the standard deviation over the square root of 36. So it's good to go. I just need a t-crit. It is 95%, but it's not 1.96. I have to calculate it for every different one. So this is a t distribution with how many degrees of freedom? 35. 95 in the middle. 0.02 on the 5 on the tail. By the way, you do not have to show your work for this. You can just put that answer down if you're comfortable doing that. Menu, statistics, distributions, inverse t, 0.025, 35 degrees of freedom. 2.03. Now I can put that in there, 2.03. So now I need to type all of this in my calculator to get the values. So 11.3921 plus 2.03. I think I got it in there right. Lower bound 11.42. Grams. Grab it up there. Put the minus 11.36. Oopsie. This is 36. This is 11.42. So there we go. We are 95% confident that the interval from 11.36 grams to 11.42 grams captures the, copy this, true population mean weight of all Oreos. I don't know, is it double stuff? Is it regular? Is it the orange kind or the green kind? I don't know. Who knows? Okay, that's it. I do want to show you, if you want to give me the formula and skip this and go right to this, you can do that on your calculator pretty easily. Again, I would encourage you to do a couple by hand, but on a test there's no sense wasting your time. To do that, we go to Menu, Statistics, Confidence Intervals. Again, the top 4 are means, this next 2 are proportions. So I'm in the top 4. I don't have 2 sample, I have 1 sample, so we're at 1 and 2. There's our Z interval, there's our 1 sample T interval. Let's say you did the Z interval. By the way, this is not the right one. Do we have the raw data or do we have the statistics? Raw data would be the weight of all 36 cookies. Nope, we have the statistics. Notice the first thing it asks for is the population standard deviation. We don't have the population standard deviation. It's a good indication that you picked the wrong function. If you go to the statistics, confidence intervals, T interval, and put in the stats, it asks you for the sample standard deviation. Well, that we have. 0.0817, sample size 36, 95% confidence interval. So it calculates the T-crit, puts it in the formula, it gives you your lower bound, your upper bound, your mean. We put the mean in, but the margin of error gives you everything. So actually this is the only 2 things you need. So that's better, that's easier. Less room for error. So it's okay for you to use it. On the packaging, the stated serving size for 3 cookies was 34 grams. Does the interval in Part A provide convincing evidence that the average weight is less than advertised? Well, 34 divided by 3 is 11.333 grams. So I do have convincing evidence that the average is not 11.333, but I have evidence that it's actually over the claimed weight. So does this provide evidence that it's underweight? No. 11.333 grams is less than all plausible values in the interval. I think that's fine. If this was an AP test, I'd want to write some more. I'd probably say something like, this is actually evidence that the cookie is overweight, not underweight. But that's probably a good thing. I mean, if you love Oreo cookies, it's a good thing, right? So there's a lot here. There's a lot you can screw up on. Let's do another one. Can you spare a square? For their final project, Christina and Rachel randomly selected 18 rolls of generic TP. And they were measuring how well this brand could absorb water. They were probably comparing the generic to a name brand, but this is just the data for the generic. To do this, they poured a 1/4 cup of water on a hard surface and counted how many squares of toilet paper it would take to completely absorb the water. Interesting. So here's the raw data. So for the first roll of paper, it took 29. The second roll of paper, it took 20, and so on. Construct and interpret a 99% confidence interval for the mean, true mean number of squares of generic toilet paper needed to absorb a 1/4 cup of water. So again, I kind of got the structure here, but there are a couple things I wanted to highlight on this one. First, P equals the mean. Mean. True mean number of squares of generic toilet paper needed to absorb a quarter cup of water. They said they randomly selected their toilet paper. Again, they probably lied, but whatever, the problem says it. Here, I think it would be, if you're going haphazardly and you're not really paying attention, you might say n equals 18 is less than 10% of all squares. That would be a mistake. They randomly selected 18 rolls, so it's less than 10% of all rolls of generic TP. Okay, this is the check I wanted to focus on. First, check the sample size. We are not big, so not there. So now we got to look at our data, our sample data, and determine if that is evidence, if that has any outliers or skewness. So we actually have to put this in our calculator and look at a graphical display. All right, so I have the data in the calculator here called TP. So let's make a display. So it looks like my data is approximately symmetric and I don't see any outliers, so we pass the check. But here's the thing. If you're going to comment on a data graph that's not given to you, you need to copy that data graph down. So I could copy this dot plot. I could copy that box plot. Or I could copy a histogram. You could even plot the normal probability plot and say it's linear, but I'm not going to do that. I'm going to do the box plot because it's easiest to graph. Long, medium, medium, medium. So long, medium, medium, medium. It wasn't quite that long. You need to have enough accuracy that it's a sketch, but enough accuracy that people that look at it can tell that you actually graphed it. You don't need to label it. The sample data is approximately symmetric with no outliers. Therefore, it probably came from a normal distribution. Therefore, the sampling distribution of X bar is approximately normal. Check. Name the test. It's a one sample. T interval for the mean was 17 degrees of freedom, 18 minus 1. So let's go shortcut here. Now I don't want to find the t-crit and plug it all in. I put down the formula. I'm just going to type this into my calculator. I already have my data in the calculator. This is going to be just a few clicks. Menu, statistics, distributions, confidence intervals. I want to do a t-interval, and I have the raw data. All you have to do is put in the list and put in the confidence level. I think it was 99%. .99 squares 2 26.9. I'm going to make this 23.0. There we go. So now our conclusion. We are 99% confident that the interval from 23 to 26.9 squares captures the, copy this down, the true mean number of squares of generic toilet paper needed to absorb a quarter cup of H2O. Okay, watch out for this check. People lose so many points on it.